Déjame respirar profundo.
Porque si la va a pensar, no se va a enterar.
¿Cómo? Ah, sí. ¿Cómo? ¿Y esto cómo?
Last talk of today is Adriana González. She talked about closest subset of P2C and Schottky.
Well, yes, that's the title. Thank you to the organizers for inviting me to give this talk in this workshop. As the title says, I'm going to talk about the closed subsets of the complex projective plane, and about Schottky type groups. I will define all of these through the slides. So, well, let's begin. This is a joint work with Valdemar Barrera and Juan Pablo Navarrete. Yes, and this work is inspired in many results that there exist in dimension 1, where we can say that if we consider closed subsets in the sphere, there are groups which are closed with some distance, whose limit set is close to that closed subset. Is a tongue twister, my talk, sorry. Well, yes, you have closed subsets in the sphere, and then you can find a group whose limit set is near that closed subset in dimension 1, and inspired by those results, we are going to make something analogous. So, as I will work in higher dimensions, I will use complex Kleinian groups. And as far as I know, the story goes like this, that, in dimension 1, we all know that there are the conformal transformations of the sphere, and they are the group PSL2C, but they can also be thought as holomorphic transformations of the complex projective line P21. Sorry, P1C. So, when thinking in higher dimensions, there are two ways to follow. One is to think about the conformal transformations of the sphere, n-dimensional sphere, or to think about the holomorphic transformations of the space PNC. Okay, so Alberto and Verhovsky, the way they followed was this one, to look at the transformations in this space, the holomorphic transformations. So they define the complex Kleinian groups as discrete subgroups of PGL n plus 1C, acting in the n-dimensional complex projective space with non-empty region of discontinuity. Okay, so this is what I said. PGL n plus 1C is a group of automorphisms of the n-dimensional complex projective space. And we are going to talk only about the subgroups of PGL3C acting in the complex projective plane, okay? Okay, so first of all, we would like to know the elements, what type of elements we have in this group. And as there has been said in many talks, we have three types of transformation. First of all is the parabolic transformation, and we are going to define them through a lifting of the transformation. So we say that a transformation G in PGL3C is parabolic if it's lifting, if it has a lift, that it is non-diagonalizable with only unitary eigenvalues. We will say that it is elliptic if G is diagonalizable with only unitary eigenvalues, or loxodromic if G has a non-unitary eigenvalue. And I made this drawing here just to remember that I wanted you to say something about the dynamics of these elements, okay? So, because this is an algebraic characterization, but there is also like a dynamical characterization. The parabolic transformation preserve a foliation given by tangent spheres in a point. The elliptic transformations preserve a foliation of spheres centered in one point, and the loxodromic transformation has the property that given an open subset, you can find, well, the transformation sends this open set to a smaller one. So in a special case where the loxodromic in the special case where the loxodromic transformation has the eigenvalues in this way, one smaller than the other, we can talk about an attracting point and a repelling point. Okay, well, now that we have the elements, we can talk. We can say some examples about subgroups of P, of PG3L3C. And one of them is Lee J told in the morning, and is PU21, the group of holomorphic isometries of the complex hyperbolic plane. Also the affine groups, which all elements share a common invariant hyperplane, and Valdemar told us about this group yesterday. And Schottky type groups that I'm going to talk about now. However, we have heard a lot about Schottky groups since yesterday, or since many years ago, maybe, I don't know. Okay, well, Schottky groups are first of all, we need like an even number of circles in the space, or compact subsets. In this case, we have circles here, and we say that two of them is paired by a transformation if the exterior of one circle is sent to the interior of the other, okay? So in this special case, I'm going to work with Schottky type groups, and the main difference is that we are not asking the exterior to go into the interior, but be contained in the interior of the other, okay? So, well, and we make this because Angel Cano showed in his PhD thesis that Schottky groups cannot act in even dimensional complex projective spaces as subgroups of this projective group, okay? So we are in dimension 2, we need another type of groups. And the type of groups we need is Schottky type groups, okay? It's a tongue twister. Okay, so, well, as I said, that's the main difference, okay? We need compact subsets, CA. We ask them to be, how did you say that? To have an empty intersection. If you send with a transformation a compact subset, we ask them to be in the interior of the other. And the diameter of these little circles here goes to 0 as we iterate, okay? Okay, so if we have transformations that satisfy all these, sigma, then sigma generates a Schottky type group. Well, basically I'm interested in the limit sets of groups, okay? So one of the first, I don't know, well, maybe the first limit set that was considered in this setting was the Kulkarni limit set that they have already defined, Valdemar defined yesterday as, well, it is the union of these three sets where L0 is the closure of points in P2C with infinite isotropy group. L1 is the closure of cluster points of orbits of points in the complement of L0, and L2 is the accumulation, the closure also of the accumulation points of compact subsets, okay? But we have another, well, I will introduce now another type of limit set that is called the Conce and Givarch limit set. Well, they work with the closure of the attracting and repelling points of loxodromic elements of the group. And well, they, in a paper that they wrote like 10 years ago maybe, that it's called limit sets of linear transformations. So we have linear transformations here. And the properties of these two sets, the Kulkarni limit set and the Konzi-Givarch limit set, is that both of them are closed subsets, G-invariant subsets of P2C, okay? Well, just an example to see that they are different indeed. I have a very simple example of a strongly loxodromic element that generates a cyclic group. And the Kulkarni limit set is conformed by these two lines that I draw here in blue. And the Konzi-Givarch limit set is just the attracting and repelling points E1 and E3. Okay, so they are different. Okay. Also, there has been someone said in a talk, maybe Waldemar also, that Angel Cano showed, like a gossip, Angel Cano showed that the Kulkarni limit set is made by lines. So these lines, if I think of them as point, they would be in the dual space of P2C. Okay, so I will be interested in closed subsets in the dual space of P2C. Okay, and we think of this space as the set of hyperplanes in C3 through the origin. Okay, and these two spaces are isomorphic, and this is the isomorphism, okay? And well, also I said that they were going to be closed, the closed subset and the limit set of some group. And well, closed in this sense, okay, in the Hausdorff distance. So we introduce the Hausdorff distance for compact subsets of a space, a metric space, and is defined as the infimum of the radius of the R neighborhoods. Okay, so we ask this, well, the set A to be contained in the R neighborhood of B, and B to be contained in the R neighborhood of A. So this is the Hausdorff distance. And well, this is the main result. That given epsilon positive and any closed subset C in the dual space of the projective complex space, such that when I think of this closed subset in P2C, it is not the whole space. Then there is a complex Kleinian group G epsilon, subgroup of PGL3C, which is not a subgroup of PU21 and neither an affine group, such that the Hausdorff distance between this closed subset I gave in the beginning and the limit set of this group is smaller than epsilon. Okay, so the idea...
The limit set?
The Konzi-Givarch limit set, yes. Okay, well, I will make a drawing to show more or less how the proof goes. And as I said, we take a closed subset of the projective, of the dual space of the projective space. So as it is closed, contained in a compact space, it is also compact. And we can take a finite cover of this closed subset. My closed subset will be this. Okay, and I can think that I have an even number of balls of radius, maybe delta, smaller than epsilon. And then I can think well, I can take a smaller disc around here, which they don't touch among them, and build a Schottky type group with these, well, with these circles, okay? So then I measure the distance between the closed subset and the limit set of the Schottky group. Maybe it was already said, but the limit set of these Schottky groups is inside these bolts. So the limit set will be near the closed set. And well, that's the idea. I just wanted to mention very fast. Of course, there are some details behind this. And another result is that for a group G acting in the complex, in the dual space of the complex projective plane, having no fixed points nor invariant lines, the limit set, the dual of the Conce and Givach limit set, corresponds to the Kulkarni limit set, this one of G, acting in P to C. So there is a correspondence between this set here and, okay, what I'm saying is this. Like thinking these in different spaces. Okay, and well, that's all what I wanted to say. This is the bibliography, and thank you very much.
Do you have any question for Adriana? Think again for Adriana.